Hello, I am glad to present our work exploiting verified neural networks via floating point numerical error. I am Kai from MIT CCL. This work is co-authored with my advisor, Martin. So let's start with the neural network. If we give it this test image from the C410 dataset, it gives us a prediction of airplane, which is correct. If we give it another image that looks the same as the first one, the prediction becomes a horse. This is known as an adversarial example, which is a well-known vulnerability of neural networks. Fortunately, we have neural network verification techniques. We can give this input image a perturbation bound, which is 2/255 in our case, and the network into a verifier. We use the MIP verify complete verifier in our research. MIP verify then claims that for all inputs within this perturbation bound of this given input, they are all classified as airplane by this network. So we know that the network is verified to be robust with respect to this particular input and this particular perturbation bound. So let's take another look at this example. The conclusion of MIP verify implies that the distance between these two input images must be larger than the considered perturbation bound. However, this is not true. So the only explanation is that the verification itself is wrong. To understand the reason, let's take a closer look at the verification of real-valued networks. We have a mathematically defined neural network, which has real-valued weights, real-valued computation, and the network topology. We also have a robustness specification to be verified. We can feed this into a complete verifier, which will tell us if the specification is guaranteed, or give us a counterexample to falsify it. However, in practice, the inference computation of neural networks has to be carried out on some inference implementations, which can use multiple hardware platforms, and there are also inference algorithm choices. There is inevitable floating point error in both the inference implementation and also the verifier. The verifiers cannot accurately model the floating point computation in the implementations due to efficiency considerations. So this discrepancy between the implementation and the verification allows us to create these counterexamples shown before. We consider 5 different implementations for the convolutional layers in the PyTorch framework. They either run on the CPU or GPU platform and can use a matrix multiplication formulation, a direct convolution formulation, or use the Winograd accelerated convolutional algorithm. We first show the floating point characteristics for these implementations. So these 5 plots show the change of a single output pixel given the change of a single input pixel for one convolutional layer. And the 5 plots correspond to these 5 implementations that we considered. So it can be seen that the change of the output is quite random given the change of the input, and the different implementations have different floating point characteristics. So based on this, we design an exploiting algorithm by using random perturbations. So we start with a safe image, which is basically a lateral image. The verifier claims that the network is robust with respect to this safe image. So we know that its perturbation space should totally fall on one side of the decision boundary assumed by the verifier. We then adjust the brightness of this safe image to obtain a quasi-safe image, whose perturbation space should be sufficiently close to the decision boundary. Within this perturbation space, we find a quasi-adversarial image that is most close to the decision boundary. Due to the discrepancy between the verification and the implementation, the decision boundaries are actually different. And it turns out that by randomly perturbing this quasi-adversarial image, it's highly likely that we can obtain an adversarial image that falls on the other side of the decision boundary of the actual implementation, but is still within this perturbation space of the quasi-safe image. So we test our method on 2 datasets. The verifier, MIP verifier, claims that the network is robust with respect to this airplane image, giving a 2/255 perturbation bound. With our algorithm, we can find other images that are classified differently by this network, but also fall within this perturbation bound. Our method also works for this horse versus deer image. We also test on the MNIST dataset with a larger perturbation bound. So our experiments have shown that our method works for all these 5 implementations considered. The table here shows the number of successfully found counterexamples for each of these implementations and each of these datasets. It's worth noting that the bottleneck here is the verification speed, because the verifier turns out to be very slow when the input is near the decision boundary. So we have to abort the computation if the verification exceeds a time limit, and this abort causes some failure cases. We have considered complete verifiers. So for incomplete verifiers, we first would like to emphasize that they can deliver fast verification by sacrificing completeness, and they are unable to prove or disprove the properties in certain cases. So it's harder to exploit these incomplete verifiers, and they do not generate the adversarial inputs, which makes our previous algorithm inapplicable. However, we still want to emphasize that incomplete verification, if it's unsound, then it provides absolutely no guarantee of robustness. To show this, we also try to exploit an incomplete verifier. So we start with a predefined input space, which is essentially a predefined perturbation around a random input. We then construct network weights for this predefined input. We select the weights and biases so that all the real units are active, which means that the inputs of these real units are non-negative. We also change these biases so that the real units are at critical points for the boundary inputs at the input perturbation space, which means that the boundary inputs, which means that the real units have a 0 input for some of these boundary inputs, so that by randomly perturbating these boundary inputs, we can probably make these ReLUs move into the inactive region. So we feed these inputs and this network into an incomplete verifier. The verifier also proves that all the real units are active, so that it can safely merge the weights before the real units and after the real units. This merge is essential to achieve a reasonable runtime. However, this merge also creates a discrepancy between the verification and the implementation, because the implementation computes the network layer by layer without the merging of the units. So this discrepancy allows us to exploit the incomplete verifier on all the considered 5 implementations. To summarize, we have shown once again that verification without considering all the implementation details is vulnerable. However, this floating point soundness issue has not received sufficient attention in current neural network verification literature. We have shown that both complete and incomplete verifiers are exploitable. And since different neural network inference implementations have different floating point characteristics, a sound verifier of floating point neural network should adapt to some particular inference implementation, and it should explicitly state the requirements for these implementations. In practice, modeling all the floating point details is very computationally expensive, so we also recommend verifying quantized or binary neural networks for promising research direction for exact, which is complete and sound verification of neural networks.